Hello. In this video, we'll be talking about the definite integral. And this is essentially a generalization from what we did in the previous section. In the previous section, we talked about how we could define area as a limit of our approximation, and our approximation was with rectangles. If I have some graph above the x-axis, I can draw a bunch of rectangles with equal width. The height of each rectangle is determined by some point on the graph. And I add all those together to estimate, and then I just take more and more rectangles to get the true area in the limit process. So this is what we're going to do. Please make sure you're doing the practice. So again, as I say, in the previous section, we saw we could approximate the area of a region by dividing its space into equal intervals, using a point from each interval to estimate the height of the graph, and then adding up the areas of a bunch of rectangles. And we got the true area by taking the limit of that process with more and more rectangles that were therefore skinnier and skinnier. So now we're going to modify this a little bit with two wrinkles. One is that the intervals don't need to be the same size. And then the other one is the function values don't need to be positive. So the picture in some cases might not look like a graph above the x-axis, but the gist is the same. So I'm going to walk you through this. This is a very technical thing. Don't feel like you have to memorize every detail, but you should understand the overall process. So we have a function f of x defined on some closed interval from a to b. And we'll divide this interval down here into n subintervals. And they don't have to be the same size. So here, A, we'll call that x0, and maybe here's x1, and here's x2, and here's x3. I'm just breaking this up. They don't have to be of the same size. Bunch more, maybe here is k minus 1, and here is k. A bunch more, and here's our last one is n. So 0 to 1, 1 to 2, 2 to 3, etc. That's n different subintervals. I could color code them if I want. Here's one, here's one, here's one, here's one. There would be one at the end. So we break it into intervals, but this time they don't have to be the same size. And let, typo here, we'll just say delta xk would be the width of the kth interval. So that would just be the kth number minus the k minus 1 number. Now, in each interval, we'll pick some value. And again, we could do this in a systematic fashion. It's probably easier if we say something like always pick the midpoint or always pick the rightmost endpoint, but we don't have to. And we will measure the height of the function at that point. So here would be the point on the graph where the x coordinate is called xk star, and the y coordinate would be f of xk star. And we'll think of a rectangle with that function value as its height. So this height times this width gives us the area of the kth rectangle. Area of rectangle number k. And then there are n of them, we add them all together. So this is basically what we saw before, this idea of adding up a bunch of rectangles to approximate something. And this is formally known as a Riemann sum. Riemann was a 19th century German mathematician who did a lot of work in terms of really nailing down the details of calculus. Newton and Leibniz had a lot of good ideas, but they didn't have a very good vocabulary for really explaining what they were thinking about. They didn't have the vocabulary of limits, for example. They just kind of waved their hands and were like, you know, it's really, really tiny. but they didn't talk in terms of limits. Riemann was one of the big people who really kind of filled in all the gaps and made sure that calculus 100% made sense and that everything was well defined. So a Riemann sum you can basically think as, oh, it's an approximation using a bunch of rectangles. But it's an estimate. If we're trying to think of it in terms of areas, the sum of the rectangles is just an estimate. To get the true value, we want to take a limit. And we would want to take a limit with smaller and smaller intervals. And here's the thing. We don't just want to say have lots of them, because in theory, I could break up the interval in such a way where one of my intervals is huge and the rest are tiny. If I have one big subinterval, and I'm approximating this graph, I could have a huge error right here, even if everything else is really accurate. So I would have all of these really skinny rectangles that are super accurate, but I have one big error in the middle. So if you want this to be accurate, you can't just say take lots of rectangles. You have to say make the rectangles smaller and smaller. So the official way we do that is we would say take the maximum, right? However big the maximum is, make that approach 0. So this is just a limit of Riemann sums. I want that phrase to sound really familiar too. A Riemann sum is an estimate essentially using rectangles. And here we're taking a limit, officially the limit as the width of the smallest one approaches 0. Or sorry, the width of the biggest one approaches 0. And this, right, look at all this notation. I mean, this is, really the epitome of what they put on the board in the background of that scene in the movie to make it look like they're doing really hard math. There is so much notation going on here. The only numbers are 0 and 1, and they barely count. Right? This is just so much notation. We abbreviate this. This whole process is what's known as a definite integral. It's the definite integral of the function f of x from a to b, and we write it like this. So it's like the indefinite integral, but you'll notice we put the endpoints of the interval at the top and bottom. So what I want you to file away right now is we already learned something called the indefinite integral. Here we have a definite integral. The names are the same, the notations are similar, but we haven't really explained how they're related. Trust me, they are. But let's just file away what we already did before with an indefinite integral. When you compute an indefinite integral, you're getting a function. When you compute a definite integral, you're doing a limit calculation, which eventually gives you a number. So I promise they're closely related, but they are very different in some fundamental ways. So I'm going to just stress some important facts about definite integrals. The definite integral represents what's called the net signed area between the graph y equals f of x and the x-axis, bounded by x equals a on the left and x equals b on the right. Net signed area means that things below the x-axis count as negative. So, for example, let's suppose the graph of f of x looks like so. And let's suppose here is a and here is b. So we want to think of a vertical line at x equals a vertical line at x equals b. And we want to think about the region between the graph of f of x and the x-axis. That might be above the x-axis, it might be below the x-axis. Now, when we did this Riemann sum, in theory, one of our rectangles was like this. It would have gone down. So right here, f of x is negative. If we had gone back to our formula, we would have noticed this is negative and this is positive. So we're not literally computing an area when we do this. We're taking a y value times a width. So it's possible that we would get a negative, and technically areas are never negative. This is what's called signed area. So when the graph is below the x-axis, we're actually getting negatives in that formula. So if I were to do the definite integral from a to b of this function f of x, I'm going to call this region 1, and this part over here, region 2. What this would compute, it's known as net signed area. It would be the area of region 1 minus the area of region 2. What I want you to keep in mind is that regions below the x-axis count as negative. It's built into the formula because some of those f values might be negative. And I'll tell you, this might seem awkward. It might seem like we're getting the area wrong, but there are so many applications of integrals that go beyond area that this, in fact, does exactly what we want to do. Maybe we'll be dealing with a velocity function, and we want velocity to be positive sometimes and negative sometimes, and integrating something negative will actually measure a certain amount of backwards motion. That is not the same as forwards motion. So we actually like that this is negative. So net signed area. It's not literally area, so keep that in mind. Also, I've talked about this earlier, it is crucial that you understand the difference between a definite integral and an indefinite integral. Definite integrals notation includes values, and those values are often called the bounds of integration or the limits of integration. As I mentioned, here we're essentially computing something like an area. Definite integral gives an area that's a number. Indefinite integral gives a function. And I promise I'll tell you how they're related. The order of the bounds of integration matters. The order, I guess that should be S. Now, typically, built into this, the smaller number comes first. We have this default of the interval AB. If you see them in the wrong order, it's not a typo. It means you're somehow measuring things backwards, and all of your delta x's were actually negative. So if you see these in the wrong order, it means that if you carefully went through the formula, you would get a bunch of negatives, and it's the opposite of the correct order. So don't say, oh, they're in the wrong order, let me fix that. It has a different meaning. But what you'll see most often, right, is when you're controlling this, you will see things like this. The default is that you'll see the smaller number on the bottom and the bigger number on the top. If the function is continuous, this limit, definite integral is a kind of limit, will always exist. You're guaranteed to be able to compute it. I'm not saying it's easy to find, I'm just saying there is an answer. And in fact, as long as the function is bounded and has only finitely many discontinuities, you can also do this. There's a word here that's integrable. So all continuous functions are integrable, and most functions that are almost continuous are also integrable. If we integrate over a single point, we get 0. You can think of this as an area problem where the width is 0. You can think of this as, here's y equals f of x, and I'm asking you, what is this area? Well, if it literally has no width, the area is 0. Another thing, and this probably makes sense, this might seem really abstract. Let me draw a picture. The definite integral from a to b represents this area. The definite integral from b to c represents this area in red. If I add them together, I get the definite integral from a to c. And in fact, This still works even if A, B, and C are in the quote-unquote wrong order. If they're in the wrong order, something is negative and we're really subtracting, but it all works out. And also, assuming we keep the limits of integration unchanged, a lot of things work out nicely. Addition, subtraction, and constant multiplication are just sort of along for the ride and they don't make anything harder. So if I have two functions added together and I want to do their definite integral of the first plus definite integral of the second. Same with subtraction. And if I have some constant multiple, I can bring it outside. This is not a product rule. This is just when we're multiplying by a constant. So we're going to learn a theorem that tells us how to find a lot of these, and it's called the fundamental theorem of calculus. I'm talking about this to get you used to it. The idea. This is a hugely important theorem. But if we understand what an integral is measuring, we can do a lot of these just using what we know about areas. So let's suppose I wanted to compute the definite integral from -2 to 1 of the function negative x minus x. Let's draw the graph and understand what this is measuring. So y equals negative x minus 3 looks something like so. Has an x-intercept at -3, it has a y-intercept at -3. Here's -2 and here's 1. So what does this mean? We're thinking of the region that is bounded by the vertical line at x equals -2, the vertical line at x equals 1, the x-axis, and this graph of, by default, I'll call this f. We're thinking about this region. It's below the x-axis, so this is going to be negative. So basically the answer here is the negative version of the area of the green region. Let me just put in some details here. Here is the point 1, -4. Here is the point -2, -1. This shape is a trapezoid. Area of a trapezoid, this is useful to know. It's base times average height, or height times average base. It's kind of your perspective. But we could think that, okay, the base here is 3 units long, but here the height is 1 and here the height is 4. It's upside down, but I'm still thinking of this as height. So this thing is 3 units wide. The height is 1 or 4, depending upon how you look at it. So that would be -15 halves after all is said and done. So here are a couple for you to try. So please hit pause and attempt these 4, and then I'll talk about them. Okay, so here we go. Let's think about the graph. Here the function is basically y equals 8. So that's a horizontal line. I have a horizontal line at a height of 8. Here's x equals 1, here's x equals 5. And this is basically saying, hey, what's this area? And it's a rectangle. It's 4 units wide and 8 units tall. This is 32. Let's look at this one. Y equals 2x. There's a line through the origin. Here's x equals 4. Here's x equals 0. Here's the x-axis. So it's the stuff above the x-axis but below that graph. And we have a triangle. Area of a triangle is 1/2 times base times height. In this case, that would be 1/2 times 4 times 8, which works out to 16. Here's 2x again, but this time from -2 to 4. Here's -2, here's 4. This is the region we're thinking about. Bounded by the x-axis, the graph, the vertical line at the left and the vertical line at the right. This area we already know is 16. This is a triangle. You can check that this is at -4. The area of that triangle is 4. But remember, definite integral is net signed area. Stuff below the x-axis counts as negative, and this works out as 12. It's 16 minus 4, not 16 plus 4. And then finally, this one. Think about the sine graph. Something like so. Here's pi, here's 0. This is what we're trying to figure. Oops, sorry, that's. Right. So this one, actually, you can only guess. You might be able to make some guesses by thinking that that height is 1, so you can kind of estimate it. If I throw a wrinkle here, so maybe you got stuck on this. What if I say 2 pi? So here, let's think about this. I've drawn this by hand, but we know there's symmetry. Hopefully you believe that this shape here and this shape here are symmetric. This one counts positive, this one counts negative. So even though we don't individually know their areas, they cancel each other out. Area below the x-axis counts as negative, so it would be subtracting the same thing. So you'll have more practice with this for homework. There are certain problems where even when you learn quote unquote the shortcut, it'll be way easier if you just think about the picture and use facts about area you already know.